Okay, I'm going to talk about the differential of log x. And I'm going to do it in 3 or 4 different ways, or I'm going to demonstrate it to you. Yeah, I guess the first way is to say y equals log x, and you'll remember that if y equals f of x, then we define the differential as f of x plus delta x minus f of x over delta x, because the top is delta y and the bottom is delta x, and we take the limit as delta x approaches 0. That's the definition of a differential, if this quantity is defined. Okay, so let's try it with f of x equals log x. So what does that give us? That gives us 1 over delta x times f of x plus delta x minus f of x equals 1 over delta x times, in this case, log x plus delta x minus log x equals 1 over delta x times log of x plus delta x over x. How am I getting that? Well, I'm using the fact that log a minus log b equals log a over b, and I'm just using a as x plus delta x and b as x, so that's nothing terribly difficult. Equals 1 over delta x times log of 1 plus delta x over x. And now I'm going to remind you that log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus and minus forever. If I think mod x has got to be less than or equal to 1, I think. Oh, I can't remember. Anyway, so in this case, log of 1 plus delta x over x equals, you see what I'm doing is looking at the log of this expression here. It's equal to just delta x over x, and then that's the first term, because instead of x I've got delta x over x, which I've just written there, minus delta x over x squared over 2 of the terms. And I'm going to ignore these because they're very small, because delta x squared is very small. So log of 1 plus delta x over x is approximately delta x over x if delta x is small, because the error terms are all delta x squared. So where's my differential? Well, my differential is this term here, which is 1 over delta x times that. So we've got 1 over delta x log 1 plus delta x over x equals 1 over delta x times delta x over x. And lo and behold, the delta x's cancel. Equals 1 over x. How about that? Recap. Y equals log x. Y dash equals log of x plus delta x minus log x over delta x. Take the limit as delta x. Limit as delta x approaches 0. Equals 1 over delta x log 1 plus delta x over x equals 1 over delta x times delta x over x equals 1 over x, QED. That's the first way to show this. We can do it in another couple of ways. I'll just do one or two of this. Another way is to define log x as the integral from p equals 1 to x of dp over p. So if we have a little graph of p against 1 over p, it looks like that. There's 1 there, and that's x. So this area here equals the integral from p equals 1 to x of dp over p, and that equals by definition log x. And so from this definition here we can see straight away that log x differentiated is just 1 over x, because when we add a little bit of area here, we just get that little bit of extra area there, and that little bit of extra area is equal to 1 over p, because it's 1 over p times delta x, I guess. So there's another way of seeing it. There's another way which I'm going to show you. If I plot the graph of, hey, that's not bad, x against y equals log x. What I'm going to do is choose x equals some value which I'm just going to make about a thin air, let's say 4. And this one here might be x equals 4.1. It's not drawn to scale, but we need to work out that extra increment there. So we go back to the standard formula of calculus, which is f of x plus delta x is approximately equal to f of x plus delta x times f dash of x. So I'm saying that the log of, I'm going to say f of x equals log x. I'm going to say x equals 4, because that's this value here. And delta x equals 0.1. And so when I substitute these values here into this equation here, I'm going to get log of 4.1 equals log 4 plus delta x, which is 0.1, that's that delta x there, times 1/4. Alright? So that's what plus a small error. Plus a small error. Alright. So let's just have a look at that. That tells me that log 4.1 minus log of 4 is approximately equal to 1/40th, because that's a tenth of 4, which is 0.025. Well, that's what it says. Let's try it on the old calculator if I can find it. Here it is. There. 4.1, where's my log? There it is. Log. 1.41 whatever. Minus 4 natural log, which is there, equals, and I claim it should be close to 0.025. Where's it gone? Let's see how close it really is. Oh, 0.02469. Pretty close, huh? So there's direct numerical verification that this ain't too bad. By the same token, I could work out log of 4.01 minus the log of 4, and just with delta x equals 0.01 rather than 0.1, that should be equal to 1 over 400 this time, 0.0025. Let's just try that, just for fun. 4.01, see that's here, log, oh it's there, minus 4 log, and again I claim it should be 0.0025 plus a small error, equals, look at that, 0.002496. So it's not exactly accurate, but you can see that the approximation is getting more and more accurate as delta x gets smaller. Okay, I think that's pretty neat. I'm going to stop there. Actually, I'm not going to stop there. I'm going to say differential of log x equals 1 over x, which rocks. Stop.